Hello, AP Stat students. Mr. Eicher here, talking about the 2018 test, question number 3, known as lefties. So we have 3.5% of children in a certain region are from multiple births. Of children born in that region from multiple births, 22% are left-handed. Of children born from single births, 11% are left-handed. So if you notice here, of the children born from that region, that's giving us basically a conditional probability. Given they're born in a certain region, 22% are left-handed. So my first thought would be to do a tree diagram. So first, are they, kind of chronologically, first, are they from a multiple birth or a single birth? And we're told 3.5% are multiple birth. So that would mean 0.06, there we go, 0.965 or single birth. And then that statement that I underlined above, of the children born from multiple births, 22% are left-handed, right-handed, or ambidextrous, I guess, but at least left or right. So 22% left-handed, and that would be 78% right-handed. And then if they're single births, 11%. Be consistent here. Left-handed, right-handed, 11% are left-handed, so that means 89% are right-handed. And the first question that I can't see on my screen right now, but the first question is, what is the probability that a child born would be left-handed? So probability left-handed, really break out the probability notation here. Not that it's required at all on the AP exam. Probability left-handed, well, that would be the branch that is the probability they're multiple birth and left-handed, or the probability they're single birth and left-handed. So the probability multiple birth and left-handed would be this branch. So multiplying those, 0.035 times 0.22 plus the probability single birth and left-handed would be this branch. So 965 times, 0.11. And multiplying those, we get the answer of 0.11385. There's no rounding rule on the AP exam. There is a rounding rule if you're typing your answer into Schoology, so I might ask you to round to 2 or 3 decimal places. But let's call this 0.114. All those people who know significant digits might be a little upset, but we'll call it 0.114. And we're going to be using that answer later on part B and C. So let's check out part B. Part B says, what is the probability a randomly selected child born in the region is a child from multiple birth? Probability multiple birth, given that the child is left-handed. So this is a conditional probability. Conditional probability. This formula is given on the formula sheet. A given B equals the probability of A and B over the probability of B. So in this context, we'd be having to find probability of multiple birth and left-handed divided by the probability of left-handed. Again, the notation can be helpful, but if you write the notation wrong, then that's no good on the AP exam. So I have my tree diagram over here. The probability left-handed we found in the earlier part of the question. We found that to be 114, I believe it was. And then the probability of multiple birth and left-handed would be that branch. So multiplying 0.035 times 0.22, that would be 0.0077. And dividing the two, we would get the probability someone's from multiple birth, given that they're left-handed, would be 0.0068. So that's our answer to B, conditional probability. So in A, we had a union of two probabilities, the multiple birth left-handed or the single birth left-handed. And then in part B, we have a conditional probability. And then next in part C, we have a binomial probability. So let's check out part C. Part C, a random sample of 20 students born in the region will be selected. What is the probability that the sample will have at least 3 who are left-handed? So a couple really important things. Anytime you have a statement that you're asked to find a probability for at least blank of blank, so in this context, at least 3 of 20, this is a really good clue. Maybe not even a clue, maybe just like yelling at you that, hey, I'm binomial and I want to be seen too. I want to be heard. So at least 3 of 20. So we need the probability 3, well, let me put the at least in there. Probability at least 3 of 20 are left-handed. So a couple things to realize here. We're being asked to find this. At least 3 would be 3 or 4 or 5, 6 or 7 or 8. All these are at least 20. And it keeps going until we get to 19 and then finally 20. That's a lot of probabilities to find. So it'll probably be much better to use the complement, the complement of this, which is 1 minus the probability of all the other cases. The other cases would be nobody's left-handed, 1 person, or 2 people out of the 20 are left-handed. We need to know the probability of being left-handed, which we found in part A. Now, if you got part A wrong, you could still get full credit on part C by using a wrong probability in part A. But the probability we had in part A was 0.114. And it is binomial. It's binomial because we have binary success and failure, left-handed, right-handed. We assume that since we're taking a random sample, that the 20 randomly selected will be independent of each other. If you're concerned about that, you check the 10% condition, then there's definitely more than 20 times 10, 200 children born in this region, is what we'd assume at least. N is our fixed number of trials, which is 20, and our probability of success is that probability of being left-handed. So all of this information on the left here is all set up. So let's now calculate this probability, and we'll do it 2 ways. First, you could do probability of 0. So probability of 0, then we need probability of 1, then we need probability of 2. Once we find those probabilities, we'll add them together and then subtract from 1. So probability of 0, you would have 20, choose 0. Left-handed probability is 114 to the 0. And not left-handed is, what is that, 886 to the 20. We'd have probability of 1 is 20, choose 1. 114 to the 1. 886 to the 19. And then 20, choose 2. 114 to the 2. 0886 to the 18. And then we find each of those probabilities and calculate, so let's do that. Alright, so the probability of getting 0 out of the 20 is 9%. The probability of getting 1 out of the 20 is 23%. And the probability of getting 2 out of the 20 is, is 28%. Adding those up, so the probability of 0 or 1 or 2 is 60%. So that means 1 minus the probability of 0, 1, or 2 would be 1 minus 60%. So the answer we get, at least to 2 decimal places, is the probability of 0.4. Now there's another approach that I'm sure you're thinking about, and that other approach is using a binomial distribution function on your calculator. Since we have multiple, we have a range, a continuous range of discrete values here. We can use binom CDF. So we would do 1 minus binom on the TI, or bin, I think it's called, bin CDF or BCDF on the Casio. But binom CDF, where n is 20, your probability is 0.114, and x is the highest number that you want, and the function is built to start from 0. So it's going to automatically start from 0 and stop at x, whatever x you tell it. So the x we want it to stop at is 2. 2. So 2. So we're going to type that into our calculator. So we would have 1 minus, let's clear this stuff, clear 1 minus second vars binom CDF. We have 20 trials. We have 0.114 probability. And the x value is the highest x value we want given the calculator starts at 0, which is 2. And the answer we get is 0.403, which earlier we got 0.40 due to rounding. So that's using binom CDF. I'll show you one more kind of trick that might be helpful for you. If you want all the individual components, the way that I did this was I went to y equals, and I think it'll work this way actually. This might be even faster than what I was going to originally show you. If you go binom PDF, and we have 20 trials, that's fixed, that's a constant. We have a probability of 0.114. And then let's just put x, this x up here, which is next to alpha. And then we'll paste that in there. And what that should do is it's going to calculate different values of x for us, so we could see them all. But to make sure our table is working correctly, we have to go second window. We'll start it at 0, because 0 is our smallest case. and we'll count by ones, so the change in the table is counting by ones, and the independent variable is automatically calculated for us, and the dependent variable is automatically calculated, so those are good. So to see these values in the table, we would type second graph, which is the table function, and notice what we have here. The probability of 0 is 0.0889, so that's 0.09. The probability of 1 is 0.23, and then the probability of 2 is 0.27. So using this function can be really helpful because you could see all the cases. You could see as we increase the number of lefties we want born in the region, it becomes really unlikely out of 20 to get, say, 20 out of 20 to be left-handed if the probability is only 0.114 of being left-handed. And then also I like this because why is 21, 22, 23 0? It's not because of like rounding that finally we rounded this to 0. It's because it's impossible. On a sample of 20, you can't get 21 who are left-handed. So this is a pretty slick trick, typing binom PDF in your calculator and just letting the calculator find different values of x. So that's pretty cool. Thanks for watching this video. Hope it was helpful for you.